Okay, this segment is designed to introduce you to simply an example of the math that goes into the building of confidence intervals. I'm going to use just some generic numbers that really don't have any substantive meaning. I just wanted to share with you the mathematical procedures that go into the calculation of confidence intervals. So the first thing I'm going to ask you to do, and if you want to grab some paper and hit pause and write this down if you want, but I'm going to ask you to assume the following things, okay? And the things I'm going to ask you to assume are a sample mean of 6, a sample standard deviation of 2, a sample size of 25, and you've been asked to build 95% confidence intervals around that mean. Again, a sample mean of 6, a sample standard deviation of 2, a sample size of 25, and you've been asked to build 95% confidence intervals around that mean. But before we go on, let's think about what confidence intervals mean. Here's my question for you. The sample mean is 6. Think about that. The sample mean is 6. Is that mean a perfect estimate, meaning is it equal to? Is that mean a perfect estimate of mu, of the population mean from which it came? No, the answer is no. And why not? Because that statistic contains error. That statistic contains error, okay? So that's why we're going to build 95% confidence intervals. And so this is very important. I know I say that a lot, but when I say this is very important, that means that's something that if possible, I want you to try and commit to memory, okay? When we build 95% confidence intervals, here's what we're saying. We're saying the sample mean is 6. However, due to sampling error, due to error, we know that that mean is not equal to the population mean. However, once we build 95% confidence intervals around that mean, we will have 2 additional numbers that surround that mean. We will have a lower limit and an upper limit, and what we can say is that while we know this mean of 6 is not perfect, this mean of 6 is not equal to the population mean from which it came, we can be 95% certain that the true population mean falls somewhere within that interval. We can be 95% certain that the true population mean falls somewhere within that interval. So, sample mean of 6, sample standard deviation of 2, sample size of 25, build 95% confidence intervals around that mean. Focus just on this first part right here. What I've done here, I've repeated the same information, mean of 6, standard deviation of 2, sample size or n of 25, build 95% confidence intervals. The very first thing I did was calculated S sub x bar. The first thing I did was calculate the sample's standard error. The sample's standard error. And one of the first YouTube clips for this week introduced you to the formula for the sample standard error. It is the standard deviation for the sample, which you already know. It's right there. The sample standard deviation divided by the square root of n. And you already know n. N is 25. So simply plug and chug, as my old professor, stats professor at University of Cincinnati used to say. Plug and chug. The standard error for the sample equals the standard deviation for the sample divided by the square root of sample size. So plug in the right numbers. Standard error equals standard deviation of 2 divided by the square root of 25. Standard error equals 2 divided by 5. That's the square root of 25. 2 divided by 5 is 0.4. Boom, 0.4. That's the standard error for the sample. Step number 1. Find the standard error for the sample. Step number 2. Consult the t-table. I'm just focusing on this portion right here. Focus on the t-table and find the correct t-value from that t-table. Find the correct t-value from that t-table. And what is the correct t-value from the t-table? It's the t-value that represents the intersection of degrees of freedom and the task at hand. The degrees of freedom in this case would be n minus 1, or 25 minus 1, or 24. And the task at hand is 95% confidence intervals. So go ahead and pause this video, consult your t-table, and verify that the table to t-value should be 2.064, which I've just placed here. A t of 2.064 is associated with 24 degrees of freedom and 95% confidence intervals. That's where that value came from. Boom. Now what do we have? We've got the sample's standard error, and we've got the t-value from the t-table. We're good to go. Lower limit is the mean minus a t-value from the t-table times the sample standard error. Lower limit equals the mean of 6 minus 2.064 times 0.4. 2.064 came from the t-table. 0.4 is simply our sample's standard error. Lower limit equals 6 minus 0.8256. 0.8256 is simply the product of 2.064 times 0.4. And 6 minus 0.8256 is 5.1744. That's the lower limit, 5.1744. Upper limit, sample mean plus t-value times standard error of the sample. Upper limit is 6, that's the sample mean, plus 2.064, that came from the table, times 0.4, that's the standard error for the sample. Upper limit equals 6 plus 0.8256, which means upper limit is 6.8256. We're done. 95% confidence intervals are 5.1744 to 6.8256. But before we go on, I want to be very clear about what these confidence intervals are stating. What these what's about to come is the story of confidence intervals. It's not a long story, but it's an important story, and it's very important that you understand this because it relates very strongly to inferential statistics. Here's the story. You ready? We have a sample mean of 6. That may or may not be equal to the population mean from which it came, from which the sample came. But we can be 95%, that's pretty good. 95% certain that the true population mean falls somewhere between 5.1744 and 6.8256. That's the end. That's the story. We have a sample mean of 6. That may or may not be equal. That mean of 6 may or may not be equal to the parameter that we're trying to estimate using this sample, this imaginary sample. We have a mean of 6. That may or may not be equal to the population mean that we're trying to estimate. But, thanks to our mathemagic, we can be 95% certain that the true population mean falls, 95% certain falls somewhere between 5.1744 and 6.8256. In the next segment, I'm going to transfer all of this information to the appropriate drawing. So stay tuned.